Okay, students, so I chose um, a question from October number 18, P11, which is of AS paper. It's a challenging MCQ. You can see here, let me read the statement of the question. A beam of light consists of two wavelengths of 436 nanometer and 654 nanometer. A diffraction grating of 5 into 10 to the power 5 lines per meter produces a diffraction pattern in which the second order of one of these wavelengths occur at the same angle theta as the third order of the other wavelength. So the first important thing is we need to understand very carefully the statement of the question. So you can see that they have mentioned here a beam of light consists of two wavelengths. So these are the two wavelengths. One is 436 nanometer and the other one is 654 nanometer. So I can just highlight these wavelengths, 436 nanometer and 654 nanometer. Okay. And then diffraction grating of 5 into 10 is about 5 lines per meter. So if you remember, there's a formula for diffraction grating. So let me write n. Lines, number of lines can be represented by capital N. So this number is given 5 into 10 to the power 5 lines per meter. So there was a formula which was a relationship between grating spacing and the number of lines. What was that? D equals to 1 over n. So if I use the value of n here, so it will be 1 over 5 into 10 to the power 5 lines per meter. So definitely when you will take this meter inverse here in the numerator, so its power will become positive. It's a negative power here, so when you will move it to the numerator, so it will positive. And 1 over 5 is 0.2 and times 10 to the power minus 5, and when I will move it in the numerator, so it will become m to the power positive 1. So I can write it meter. So it means D is, which is grating spacing, diffraction grating spacing, that is 0.2 into 10 to the power minus 5 meter, or even you can write 2 into 10 to the power minus 6 meter. So this is basically the first thing which you got from this information which is given here, number of lines per meter. Okay, and then further they have mentioned that it produces a diffraction pattern in which the second order of one of these wavelengths occur. Second order. This is very important information. Second order of one of the wavelengths. So we have a grating formula which is d sine theta equals to n lambda, where d is grating spacing and we have calculated that. Sine of the angle theta, theta is angle of diffraction, and small n represents the order of diffraction and lambda is the wavelength. Now I have already calculated d, so I can just find out 2 into 10 to the power minus 6 into sine of the angle which we need to find out equals to second order. Second order, for second order small n should be 2. So 2 multiplied by the wavelength. So we have to choose one of the wavelengths. So we will choose this longer wavelength. For example, it will be 654 nanometer, means 10 to the power minus 9 meters. Nano means 10 to the power minus 9. Now after simplification, you can see this 2 can be cancelled by this 2, and I can take this 10 to the power minus 6 on the other side. So it will become sine theta on the left, at the left side, equals to 654 into 10 to the power minus 9 times 10 to the power positive 6. Obviously the sign of the power will be changed when you will take it on the right side. Okay, then further you can simplify it. So it will be 654 times 10 to the power minus 9 plus 6 would be 10 to the power minus 3. So sine theta is equal to 654 into 10 to the power minus 3. Or in other words, I can write 0.654. So sine theta is equal to 0.654. So theta would be sine inverse of 0.654, and you will get answer of it after solving on calculator. It will give you 40.8 degrees. So similarly, now I need to do the same working for the other, you can say, order. They are mentioned here. Uh, where were we? We were here till this part of the statement. At one of these wavelengths occur at the same angle theta as the third order of the other wavelength. So third order, so it means I need to use d sine theta is equals to n lambda again, and d was 2 into 10 to the power minus 6 into sine of theta. Now for the order, now we have to use third order, which is 3, and the other wavelength. The other wavelength was 436 nanometers. Nano means 10 to the power minus 9. Okay, now I can simplify. 2 ones are 2, 2 1.5s are 3. So it means it will be sine theta equal to 1.5 multiplied by 436 will give you 654 into 10 to the power minus 9, this one, and this power 10 to the power minus 6, when I will move it to the right side, so it will be 10 to the power positive 6. So again you will get 654 times 10 to the power minus 3, and in this way you will find the same angle 0. Sine inverse of 0.654, which will give you the same angle, which is 40.8 degrees. As it has mentioned here in the question, that diffraction pattern in which the second order of one of these wavelengths occur at the same angle theta as the third order of the other wavelength. So same angle theta means you are getting the same value of the angle, even for by using the third order and the other wavelengths. So this could be the answer, 40.8 degrees and 40.8 degrees, you are getting the same angle, and 40.8 degrees, answer C. Thank you very much, students. I hope it will work. Thank you.